Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. As a part of our discussion on various organometallic catalysis reaction, we have been looking at oxidation reactions of ethylene or olefins in the last two lectures. We have started off by looking at Wacker oxidation, which is a long known reaction, has been known in the industry for over a century now, and in which ethylene is converted to acetaldehyde in presence of palladium catalyst and copper catalyst in presence of molecular oxygen. We have also seen another important industrial process in the form of Halcon arco-oxidane synthesis, in which epoxides, propylene oxides were formed using a molybdenum catalyst. Now, in our last lecture, we have discussed about the possibility of this molybdenum 6 oxo species transferring the oxygen from molybdenum onto propylene by possibly two pathways. The one involved direct transfer of oxygen to the olefin, and the other involved the transfer of the eta 2 type propene peroxo species to coordinated olefin, resulting in the formation of propylene oxide. So, continuing further on this epoxidation reaction, we are going to talk of another interesting epoxidation reaction, which is better known as Enantioselective Sharpless epoxidation reaction. And this is catalyzed by titanium and thus performs the epoxidation of allylic alcohol. And this is beautifully represented by this example R1, R2, OH, R3, T butyl hydroperoxide, CH2Cl2, 20 degree centigrade, and this is catalyzed by titanium tetraisopropoxide, and the reaction in presence of a diethyl tartarate gives two different forms of epoxides R2, R1, R3, O. and the opposite form is obtained with plus diethyl tartarate. The yields are extremely high, 70 to 90%, and Enantio selectivity is more than 90%. Now, this is a very nice example of Enantio selective epoxidation reaction reported by Sharpless, in which one can see that by taking two different chiral ligand ancillary, that is with minus DET they get the epoxides where the oxygen is attached from the top, and where with plus diethyl tartarate the opposite enantiomer is obtained. And so, one can see the scope of this epoxidation reaction extending to asymmetric catalysis. So, another example of Enantio selective epoxidation involves alkyl and aryl substituted alkenes undergo enantioselective epoxidation. And this is given by R1, R2, R3 with an oxidizing agent IO in presence of a chiral silane manganese compound in acetonitrile at 25 degrees centigrade yields this chiral epoxide R1, R3, R2, oxygen plus iodine, and this was reported by Jacobsen, and the active species of this is consistent is thought of as a manganese oxide compound, and this can be act as a catalyst. So, chiral silane manganese 2 complex acts as the catalyst in enantioselective epoxidation which is converted to silane manganese 5 oxide, and this is beautifully represented by the schematic mechanism Mn star L, presence of oxidant giving Mn star manganese oxo species and that reacts with this olefin to give the desired propylene oxide. So, the transfer of oxygen atom to the alkene occurs without the participation of the transition metal carbon intermediate. The transfer of oxygen atom to alkene occurs without the participation of TMC intermediate. Now, this is a very interesting observation in the sense that a highly enantioselective epoxidation can be carried out with chiral silane manganese complex, which can transfer the oxygen functionality onto the olefin without the olefin formally getting activated by binding to the transition metal. So, with this we come to this important closure of this important epoxidation reaction in the form of halcon arco oxygen epoxidation reaction. To sum up what we had observed is that this epoxidation reaction is an important industrial method for producing propylene oxide, and this uses molybdenum 6 catalyst which carries out this conversion of propene to propylene oxide. The utility of this reaction can be gauged from very high annual turnover of around 3 million tons per year of propylene oxide being produced by this method. Now, we have also seen the scope of this extension being extended in form of enantioselective epoxidation reported by Sharpless, where titanium tetra isopropoxy catalyst in presence of chiral ligand like diethyl tartrate produced different isomers of epoxides depending on the chiral ligand that they used, and these reactions were carried out in large scale, high yield and high enantiomeric excess. And then we have also seen the development of a chiral silane type catalyst that also carried out this epoxidation of olefins, trisubstituted olefins using a manganese chiral silane compound in high Enantio selectivity. So, with these one can sort of see how these important reaction of epoxidation have been used not only in industry, but also have been extended for carrying out the epoxidation in enantioselective fashion. So, with this we come to the closure of this oxidation of olefin reaction, and we are going to take up two more important reactions which are water gas shift reaction and Fischer-Tropsch reactions. Now, before we start discussing these reaction in detail, it is important to know that the industrial perspective on these two reactions. As mentioned earlier in couple of discussion back, we had looked at industrial perspective of the field of organometallic chemistry in terms of the metals that would be used in carrying out many of the industrial scale reactions, and what we had observed that by and large palladium stands tall on that front, in the sense that palladium is quite indispensable with regard, not only with regard to CC bond formation, but also can be used in industrial processes for oxidation reaction. And a glowing example of that is that of Wacker oxidation, where ethylene is converted to acetaldehyde in presence of molecular oxygen and a co-catalyst in form of copper. So, what we see that from industrial perspective, palladium is the metal of choice for organometallic catalysis, and as far as the feedstock being concerned, ethylene is also important substrate in terms of various industrial processes. Particularly with respect to ethylene, we have seen addition reactions, hydroboration, hydrosilylation, hydrocyanation reactions. We have also observed oxidation reactions like the water process. So, what it turns out that the ethylene is an important substrate from the perspective of industrial transformations, as ethylene can be converted to various intermediates like aldehydes, alcohols, acids, and depending on further utility, they can also eventually be used for making important target molecules. Now, as far as the substrates are concerned, after ethylene, what is the focus of industrial perspective is that of carbon monoxide. Now, it is in this context of carbon monoxide that water gas shift reaction and Fischer-Tropsch reaction becomes relevant. So, this carbon monoxide can be converted to useful chemicals using redox chemistry, which might involve reduction of carbon monoxide or oxidation of carbon monoxide, and the chemistry which comes out of it is thus called C1 chemistry. So, this C1 chemistry of carbon monoxide gradually becoming important as raising concentration of carbon monoxide has turned to be a global nuisance, and there is active research in finding out ways and means to utilize carbon monoxide for some gainful purpose. So, in this perspective, the utility of ethylene chemistry in terms of Wacker and other industrial processes, there is a emphasis of those getting substituted by that of C1 chemistry, and from this standpoint alone, this water gas shift reaction and Fischer-Tropsch reaction thus becomes intuitive. So, it is important to mention that these two reactions are counterintuitive. Water gas shift reaction is the oxidation of CO affects oxidation of CO and Fischer-Tropsch reaction affects reduction of CO. And as mentioned earlier, though the Wacker process has opened up the doorway for organometallic chemistry, later the C1 chemistry or the chemistry used with CO is becoming important. The C1 chemistry or CO based chemistry is gradually becoming important, though Wacker process, this is with ethylene C2H4, is long known. So, this is an important paradigm shift in terms of utility, in terms of the perspective of industrial chemistry, because as the natural gas gets deployed, the source of ethylene becomes less, and then one needs to find alternate route for making all these important chemical using the oxidation chemistry of olefins or other forms. And in from that perspective, this water gas shift reaction as well as Fischer-Tropsch synthesis provide a viable and attractive alternative, as there is an acute need for utilizing the increasing concentration of CO in the form of its oxidation and reduction to give the oxidized and reduced products. So, from this perspective alone, we are going to take up these two reactions, and to begin with we are going to first look at the water gas shift reaction. Now, before doing that, this CO is an important, CO and hydrogen are important constituents of synthesis gas, and these synthesis gas are used for various industrial processes. CO is an important constituent component of synthesis gas, along with hydrogen, and can be obtained, and synthesis gas can be obtained by several pathways. One, the controlled oxidation of crude oil. So, in this when crude oil contains several mixtures, so when in the controlled oxidation of the crude hydrocarbons, CO and hydrogens are the synth gas is obtained. Reforming, second is reforming of natural gas. Gases, and this is which essentially consists of mainly of methane, and this is illustrated by the equation CH4 plus H2O giving CO plus 3 H2 delta H plus 205 kilojoule per mole, and CH4 plus half O2 CO plus 2 H2 delta H equals minus 35 kilojoule per mole. Now, so one can see that the reaction of methane with oxygen can generate carbon monoxide and hydrogen, which is nothing but synthesis gas, or direct oxidation of methane with oxygen can also give carbon monoxide and hydrogen. And the last method for this is gasification, cold gasification. Which is given by C plus H2O giving CO plus H2 delta H equals plus 131 kilojoule per mole. So, with this I would like to conclude today's discussion on water gas shift and Fischer-Tropsch synthesis. To summarize, in today's lecture what we had done is we had looked at the various scope of this epoxidation reaction, particularly with respect to enantioselective epoxidation reaction. And in this regard we had looked we have discussed about Sharpless epoxidation reaction using titanium tetraisopropoxide catalyst and a chiral auxiliary, and which is diethyl tartarate, which in one enantiomeric form give one kind of epoxide, and with the other it gives another form of epoxide. Moving on from Sharpless epoxidation, we have also looked at the epoxidation process reported by Jacobsen, in which a chiral silane manganese compound in presence of benzene iodine oxide derived reagent could affect enantioselective epoxidation reaction. Now, after finishing off with the olefin epoxidation reaction, we move to initiate discussion on a very important part of the part of a chemistry, which is called C1 chemistry, or the chemistry of utility of carbon monoxide. And in this context we have discussed water gas shift reaction and Fischer-Tropsch reaction. And what we noted is that these two reactions are nothing but redox chemistry of CO with the water gas shift reaction affecting oxidation of CO and Fischer-Tropsch reaction affecting reduction of CO. Now, this CO chemistry is important with respect to this synthesis gas, in which it is a component of, and then one looks at the various reactions which leads to the formation of CO in the synthesis gas, and this can be obtained by three reaction. First can be controlled combustion of crude oil, the second is reforming of natural gases, and third is coal gasification reaction. So, these three reactions contribute to CO in syngas, and we are going to look at various methods, particularly a water gas shift reaction and Fischer-Tropsch synthesis, that would focus on utilizing the CO of syngas to convert some valuable industrial chemicals. So, with that I conclude today's lecture. I once again thank you for patiently listening to me in this lecture, and I look forward to taking up this topic of water gas shift reaction and Fischer-Tropsch synthesis is in bit more detail when we meet next. Till then, goodbye and thank you.